A few months back when Ron asked me to submit a presentation, I asked him only one question, which I thought was the only important question. Will there be beer there? And Ron said, it's at a pub, eh? So that's excellent. The venue's been great. Thank you very much. What I should have asked is, will there be snow? Because I was completely unprepared. All right. My name is Brandon Enright, and I'm a security investigator with Cisco Systems. I wanted to give a presentation that was really fun and awesome and about reverse engineering or hacking or taking over a botnet, or the type of presentations that I like to see and the ones I like to give. But almost all of us beyond our hobby and security in technology have to be employed in some way. And so this presentation is about the defensive side of security, and hopefully this presentation is very helpful for your day-to-day job, finding bad guys on your network, finding malware, that sort of thing. It will hopefully be a lot more useful to you guys if you ask questions. I don't have a full hour of content here. Interrupt me at any time for anything. It'll really make it a lot better. And if you're not drinking, we're not going to make it through this presentation. So a little bit about me. I'm a hacker. I used to think that I was a programmer or a developer, but I've learned after a number of years of seeing actually good programmers and people who really do development and think about maintainability and documenting the code, I'm neither. I can hack code. I can write some really cool stuff, but I'm not really able to program or develop at a professional level. I'm a problem seeker and solver. I love puzzles. I love math challenges and that sort of thing. That's where I spend most of my time. I'm a Linux user. I've been a full-time Linux as my desktop user for more than a decade now. I'm a extreme twisty puzzle enthusiast, so that's Rubik's Cube style puzzles, both building them, designing them, and solving them, and all of the math behind them and programming them and all that stuff. I used to be an Nmap developer, but just the realities of a busy life means that I'm more of an Nmap evangelist at this point. And actually, that's how I met Ron. I was a big Nmap developer, and Ron came along one day and just started writing a whole bunch of Nmap scripts, incredibly useful Nmap scripts, I should add. And that's how we met. I like to do a little bit of armchair physics, so I read a lot of physics books and that sort of thing. I'm kind of a mad scientist, so my kitchen is a little laboratory, think Breaking Bad, but without the drugs. I'm a crypto nerd. I wish I were better at crypto, but I've tried to grow the beard, and I just can't really reach a crypto beard. So I work for Cisco. I've been at Cisco for almost 3 years now. Cisco is a very, very, very large company. Cisco has 400 sites in over 100 countries. It's actually like 110 countries. What this means is that the sun never sets on the network. There's always users at work doing their job, and it also means that we have traffic to almost every country in the world legitimately, and we have customers in every country in the world. Even if we weren't able to sell them to them directly, they ended up getting our products some way or another. So the typical, if you don't have users, or if you don't have a business reason to do traffic in China or Pakistan or wherever, that doesn't really apply to a company of our scale. These numbers are from 2010, so you can imagine how much they've changed. In 2010, we had 130,000 Windows machines on the network, and we had 90,000 Linux machines. This doesn't account for phones at all. It doesn't account for all of the personal devices people are bringing in general. The company's moved to a bring your own device style initiative where people can put any machine on the network and it's within policy. And just general company growth and technology growth, these numbers are a lot larger now. There are 40,000 routers and switches on the network. Now, if you're thinking, how the fuck do you have 40,000 routers and switches on the network? We're a networking company. So imagine a whole bunch of people in Cisco asking themselves every single day, is there any chance our router or switch is kind of, sort of, almost maybe going to solve a part of my problem? The answer is yes, you should install a router. And that's been going for Decades. The network is so overbuilt. We have routers that are 100 times more powerful than the little task that they do, so we need 2 of them just in case. Now, big networks, and this applies to ISPs, it applies to Cisco, it applies to any large network. So we're not unique, because we're a networking company, that doesn't make us unique. Big networks are very, very, very hard. You have every version of every piece of software ever released. So we have like every version of Windows, every version of Solaris, every version of FreeBSD, OpenBSD, NetBSD. We have every version of iOS. Everything that you could imagine someone is running, even if they shouldn't be running it, they're still running it. We have a bring your own device initiative, and now this is part marketing and sales in the company, and part, we practice what we preach. But anyone can put their personal cell phone, their personal laptop, their any device that they want on the network, no questions asked. We have every version of every smart and dumb phone. As long as you can get a TCP/IP stack on it, it's on the network. We have thousands of VPN users at all times. Now this does not really capture the sort of the scope of how many VPN users we have on the network. Because we make networking equipment, we make hardware VPN devices, there are tens of thousands of users that have a hardware VPN device in their home, and it broadcasts the Cisco wireless network into their home, and all their computers in their home are plugged into it. So there is no such thing as 5 o'clock, everyone goes home, the traffic doesn't stop, because they just go home and all of their personal web browsing and that sort of thing is on the network, all their wireless is on the network. Now, only the person in the house who is an actual Cisco user who has the Cisco ID that can authenticate, ostensibly they're the only one that's on, but we all understand the reality is that everything is on the network. The sun never sets on the network, there is no downtime, it's a global company, it's a global network. And the amount of logs that our network generates, and this is after filtering, is beyond what a single system could ever hope to manage. That means we're doing a little bit more than a terabyte of logs a day, and you can't realistically build a system, a single system, to handle that kind of load. Now, if you're wondering, do I have a big network or not? There's a simple test you can ask yourself. Is it possible for you to memorize all of your IPv4 prefixes announced by your BGP router? Cisco has 74 different prefixes. That's 1.17 million different IP addresses, not really memorizable. I used to work in an organization that only had like 6 prefixes. We had a lot of IPs, but we only had like 6 prefixes. It was well within sort of mental scope. If you can look at an IP address and go, oh, that's definitely a IP address within my organization, then you have a small network. If you can look at an IP address and go, I don't know, maybe it's a Cisco address, maybe it's not, then you have a big network. All right, so this talk is about finding bad stuff on your network. If you want to find bad stuff on your network, you need to have the telemetry, you need to have the logs, you need to have the data that will actually help you find that information. There's essentially 3 different main tiers that you could collect logs. Of course, you can collect logs at the host level if you have managed hosts, if you have antivirus running on the hosts, if you have like host intrusion prevention software, HIPS software, if you have an incident response agent like either Mandiant or Google Rapid Response, or there's others I can't think of right now. You can collect logs at your IT infrastructure level, so you can collect your DHCP logs, you can collect your wireless logs, you can collect your DNS logs. If you're doing like DNS RPZ response policy zone, or if you have a DNS sinkhole, you can collect those logs. You should collect VPN logs. Your AAA logs is your authentication and authorization and accounting logs. And you should collect server syslog for any important critical servers on the network. And then of course at the network layer, there's NetFlow, which is, think NSA, it's just metadata. Well, presumably the NSA has more than that, but let's pretend that it's just metadata. And hopefully on your network you have some sort of transparent web proxy or some other means of seeing all of the HTTP traffic on your network. That could be like Bro IDS reconstructing all the HTTP streams as they go by. It could be a Blue Coat. It could be a Cisco WSA, a web security appliance. It could be a a WebSense box. It could really be anything that can get you these logs. And then presumably you still have an IDS or an IPS or something that's firing alerts based on signatures. And if you're going to collect these things, you need to put them somewhere. This is the quote-unquote big data. You could put them in something like Splunk. You could put them in something like Hadoop. But ultimately, you have to put all your logs, or the majority of your logs, all in one location that is somewhat fast and somewhat easy to access your data. Because if your data is not fast or easy to look at, you will not use it to its fullest. Because you'll be sitting there, and let's face it, everyone has a huge amount of stuff that they need to do during the day. And so you can be like, I don't have anything to do for the next 15 minutes. I should look for bad stuff on the network. And if looking for bad stuff on the network means, oh, well, then I got to get the logs from here and the logs from there, and then I'm going to have to pull them down and grep them, and it's a big pain in the ass. You just won't do it. So it has to be as easy as possible to get. It has to be fast to get, and you have to be able to get almost all your logs. Otherwise, you will not utilize them as much as you should be utilizing them. Now, big data is going to solve all your problems. There's a fantastic slide by David Arley. I wasn't the one that took this picture, but it is, I got to read this to you guys. This is David Arley. He says, big data is like teenage sex. Everyone's talking about it. No one really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims that they're doing it. Big data is a marketing bullshit term. Now, putting all your data in one location, that's not a new idea. Technology has made it possible. Marketing has turned it into big data. But putting all your data in one location doesn't mean you're getting any value out of it. And then so that brings us to the next topic. SIM, security intelligence event monitors, or security whatever, I don't remember. Doesn't matter. If you look at all of the different SIM vendors and you look at their documentation and you look at their websites, every single SIM vendor uses this word correlation. Now, I'm only going to read you one of these. This is from the ArcSight website. It's under the correlation section. It's like the top header on their website. HP ArcSight Correlation Optimization and Retention Retrieval Engine, CORR, is a breakthrough technology that delivers orders of magnitude improvement in log correlation and storage, helping security administrators to thwart the complex threats they face today. HP ArcSight ESM solutions use this core engine as the foundation to help security teams keep up with the speed needed for today's threat detection, security analysis, and log data management. Now, sounds good. What the fuck does correlation mean? Now, if you're really dumb, or if you're just not a security engineer, you're probably thinking correlation, oh, that's got to be some magic, proprietary, genius stuff that takes your logs and gives you magic out of it, you know? So if you're dumb, that's what you think. And this is why correlation is such a fantastic marketing term, because if you're really smart, if you're a good security engineer, you're thinking, well, it can't be bullshit, right? It has to mean something. And so you're thinking, oh, well, we could take the timestamp of the something or other log, and we could add a little fudge factor to it, and then we could take the timestamp of some other log, and we could try to correlate the length of this with the timestamp of that, and we could build this graph of activity, and then using some graph traversal algorithm, come on. That is not what they're doing. And if you're a marketer, you think that correlation just prints you money, because basically it does. What is correlation actually? It's a frickin' join. You have a relational data set. You have a common field. Now, sometimes the common field is actually time, so I call it a temporal correlation, because it's not a common data like an IP address. It's just a timestamp. But it's a join across multiple data sources that share some common field, or some field that you can map that field from one data source into another data source. This is like Microsoft Access days. Welcome to 1990. Your brain is going to beat a SIM already produced correlation engine every day. Your brain is always going to beat it. If you understand how a union, a join, an intersection, or any other basic data relationship works, You're the one who understands your network. You're the one who understands your data sources. You're the one who understands what your hosts should and shouldn't be doing. You're the one who understands what's important to your business, and you're going to build reports that are way better than anything a SIEM vendor can ever give you. Now, that's not to say that SIEM isn't useful. You do need a way to get your data. A SIEM solution does give you the ability to extract, run queries and run reports on your data. So what basically I'm saying is this presentation goes beyond the marketing aspect of SIEM or network intelligence, and it goes beyond the canned reports and the automated stuff that's supposed to find stuff on your network but isn't realistically going to find anything that you couldn't have already found yourself. And this presentation is all about looking at your data and finding the stuff that you want to find. Now, you have logs. Let's gold mine them. Now, within Cisco, we organize all of our monitoring into what we call a playbook. And a playbook is this sort of framework that builds all of these. So we have like a report objective. We have how to analyze the report. We have the actual query across all of our data sources that generates the results. And we have all the documentation built into it. I thought about giving a presentation on our playbook approach to organizing our monitoring, and I thought it would just be too boring for a hacker audience. The only important aspect of the playbook for what I'm going to talk about today is the two different types of reports. There's the high fidelity, and there's the investigative. Now, ultimately, the goal is always going to be, let's make a high fidelity report, as few false positives as possible. High fidelity reports are the ones that don't have any realistic chance of producing a false positive. They can be fully automated. A human being doesn't need to look at them in any way at all, and they just produce bad stuff that can just be immediately acted on. That's always the goal. Unfortunately, it's not realistic in the general case, or it usually isn't realistic in the general case. You can make very, very, very specific high-fidelity reports. Think of sort of antivirus style. You can create a frickin' MD5 sum of some known bad binary. No chance of false positive there, or very little chance. But flip a single bit and you completely miss it. So it's a high-fidelity report, but it's so specific that it's not particularly useful in the field. And then there's investigative reports. Those are everything else. That's where a human being needs to look at it and vet the results. Now, I gotta warn you that even when you think you've made a high-fidelity report, statistics is not on your side. The Bayes theorem, to get a little bit of computer science crap in here, I just stole this straight from Wikipedia. I'll read it to you guys. Hopefully this isn't new material. Hopefully it'll be like, wow, that's kind of cool. But maybe it'll just be something you've already heard. So let me read this. This is Wikipedia on the Bayes theorem. So suppose you have a drug test that produces 99% true positive results for drug users. That means if you're taking a drug, there's a 99% chance that the test will detect that you're taking that drug. Suppose also that if you're not taking the drug, the test has a 99% chance of not flagging you as taking the drug. So that is, it's a 99% accurate test, 99% chance that it will detect if you're taking it, and a 99% chance it won't detect if you're taking it if you're not actually taking it. Now suppose that 0.5, 0.5%, or 1 in 200 people in the population are actually taking the drug. If you test people at random, and the test says that they're taking the drug, what is the probability that they're actually taking the drug? Now remember, this is a 99% accurate test. You would think that it would be a really high percent chance that they're taking the drug. Turns out that there's actually only a 33% chance that they're taking the drug, a 66.8% chance that it's a false positive. Now, if that seems kind of weird, there's a whole Wikipedia article on it that explains why it's true, but it's true. And so when you're creating a high-fidelity report, or a report that you want to think is high fidelity, if you're going through millions or billions of log entries, you have to have extremely, extremely accurate, no chance of false positive queries, or you're going to have lots and lots of false positives, a lot more false positives than you think. I can't tell you how many times I've created a query where I thought, okay, this has got to be high fidelity. There's no way that these sets of these indicators could all come together And we get false positives all the time. It's like 10 false positives to 1. Like, how is this possible? And then we start making like, exclude this, exclude this, exclude this, and then we go, okay, we have to go back to the drawing board. Maybe this is not actually a high fidelity report. Okay, so this talk is not about 100% effective ways to find malicious activity. This talk is about the ideas that you can use, that you can apply to your data to get you started. If I were just going to give you a bunch of 100% effective, you could find malware doing this, 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 I'd be basically giving you a whole bunch of high fidelity reports that are super specific, but not broad enough to really apply to your network. So this talk is about ideas. And so when I present an idea and you guys have any questions about it, I'd love to hear them. Okay, now I don't know if you noticed or not, but HTTP is the internet. Every user, if their web browser doesn't work, the internet doesn't work. Doesn't matter that anything else works, the internet doesn't work. Because HTTP is the internet to every user, it means every organization allows HTTP out. It means that almost all private IP addresses on your network use a web proxy so that they can go and get their updates, so that they can go and do Google searches, so they can go and wget down latest Debian packages, whatever. Almost everything allows HTTP out. In fact, HTTP is so ubiquitous that it's practically the new TCP. It's practically a transport protocol. Because of this, all of the different factors have come together to make the web the most common way to deliver malware, because your browser has a gigantic attack surface. You have a parser for HTML, you have a parser for CSS, you have a parser for JavaScript, you have a parser for PDFs, you have a parser for Shockwave, Flash, Java. Your web browser is like a freaking operating system. So it's a gigantic attack surface, and it speaks the one protocol that is basically guaranteed to always get out, which means that malware gets delivered to your machines via HTTP, and malware uses HTTP predominantly, most malware does, as its command and control mechanism, the mechanism it uses to send data out, to get instructions, that sort of thing. This means that HTTP logs are the most valuable data source that you're going to have available to you. If you want to find bad stuff, if you want to find exploits, your HTTP activity on your network is the best place to go for that. Now, web browsers are one product, one program, one set of things that speak HTTP, and then there's all the stuff that isn't a web browser. So one of the good ways that you can start to get a handle on your data is ask yourself, what does a browser look like versus what does everything else look like? And so to understand what does a browser look like, you need to understand what browsers do, that they always do, that all browsers do, and there's a certain set of things that all browsers do. All browsers set a user agent header, a user agent string. All browsers set a referrer header whenever they're being referred to a page. Basically every browser, at least in 2013, every browser uses HTTP 1.1. No web browser uses 1.0 at this point, even through a proxy. And browsers have a lot of idiosyncrasies. Almost every browser has an accept type that says, I accept HTML, I accept XML, I accept whatever. And they almost all set like connection, keep live, connection close, connection whatever. And there's a whole bunch of other settings. There's no reason that you need to do any of these things if you just want to speak bare bones HTTP, and a lot of things don't. So I know you guys can't read this, so I'll explain it. We store all of our data in Splunk, so this is a Splunk query that says, show me all of the activity in our web logs where a user agent header was not used. So it is just a super generic query, and I said, let's show me the top 10 results. I duplicated by IP address. And result number 9, that machine's pwned. This is the top 10 results. We have millions and millions and millions of results a day, so you can imagine that this is going to find a lot of compromised machines if there's one even in the top 10. This machine is actually doing click fraud. So there's a piece of malware on the person's machine that is it's causing their web browser to visit advertisements in such a way that the person who's registered as the advertising affiliate gets a revenue stream. So they're basically just defrauding some advertising company and making some money. Go for it. Yeah, so of course you're going to go through some investigative process. So now you've found, there's the one thing that stands out as definitely bad. So you're going to go through an investigative process, figure out what other activities is this machine doing. Can I identify the malware based on the command and control URLs that it visits? Is there any way that I can block or blacklist the command and control, the IP addresses, the domain names, that sort of thing? Can I get a name of the malware? If I can get a name of the malware, maybe I can search my antivirus logs for it. So you're going to go through some sort of investigative process for this particular machine. Now, what I've shown here, this is not a report. This is not to the fidelity that you would actually ever consider running on a day-to-day basis and analyzing these logs. This is an example of the starting point that you would use for creating more specific reports. So this is an idea, this is the tip of the iceberg, and you're going to create a whole bunch of other reports that are sort of based on this idea. So no, I wouldn't go and exclude, because ultimately I'd be doing this and some other activity, and there's a whole bunch of possibilities. But the fidelity of this, even though there's an infected machine in the top 10, is still, if only 1 in 10 results is a positive, that's going to take a lot of investigative, a lot of analysis time. It's probably not worth doing. So this is really just an idea. It is not a fully flushed out, fully documented, fully prime time type of report. Okay, web browsers are very, very quirky, but they're very, very consistent in their quirks. So within a specific browser, Internet Explorer, Chrome, whatever, or even within a specific version within a browser, Internet Explorer 8, Chrome 30, whatever, they do certain things the same way every single time. Like, they have the same order of HTTP headers. Something or other header comes first, something or other header comes second. And you can imagine why, because there's some set of code that is constructing this request. And whether it's a state machine or it's just first I do the user agent string and then I put it into my little string buffer or memory buffer, this string, this string, this string. There's some consistent, deterministic thing that they do for constructing a request, and they do it the same every single time. Within a header, you can have headers that take parameter lists. So I know you can't see this, but there's an accept header down at the bottom. First thing it accepts is text HTML. The next thing it accepts is application XHTML plus XML. Next thing it accepts is application XML. Next thing it accepts is Q 0.9. No idea what that is. But there's some order to the parameters within the header, and it's consistent. Quirks are incredibly difficult for malware to emulate without literally ripping all of the code out of the web browser. They're not going to be able to fully emulate all of these quirks. So you can ask yourself, okay, so the example I have here, it looks like Chrome. It's not Chrome because the header order is wrong. So this is just an idea, and I haven't shown you all the code that would implement this. And in fact, if you're using a web proxy device where it's just giving you logs, you may not actually see the order of the headers because you may not see all the headers. So I don't have this in production looking at our web logs, but I have in the past used this to great success for finding stuff via IDS signatures that enforce a header order in the IDS signature, and you can find malware that way. It's a good idea, it's a good starting point, but this idea has to be fleshed out a lot more for the specific thing that you're looking for. Now, there's other things that browsers will tell you, and you just do a simple sanity check. So let's look for browsers that are telling us that they're Internet Explorer. Because when Internet Explorer tells us that it's Internet Explorer, it does it in a very specific way. So I just did a simple query in our logs, show me all the stuff that's using a user agent string that contains the string Internet space Explorer. And then we have a couple results down here. This thing says my user agent string is Microsoft space Internet space Explorer. No, you're not, because Microsoft Internet Explorer presents a completely different user agent string. This is probably bad. If you find something that looks somewhat suspicious and then you catch it in a lie, it's probably really suspicious. And this is malware. This is malware command and control. And there are I only showed you 2 results because I can only fit 2 results on the slide, and you still can't even read them even with 2 results. But this you will find just hundreds and hundreds and hundreds of pieces of malware. So you can turn around and you can create really very specific queries, very high fidelity queries to find all this stuff. You can build up a corpus of queries like this that will find just insane amounts of malware on your network if you have a large network. Okay. Now you may want to do something a little bit fancier than this. Instead of just going, hey, let's just take a look at who's telling me that they're Internet Explorer. Let's actually do some real fact checking here. Let's take a look at user agent strings from Internet Explorer, and I've included a few here. I'll read one for you. This user agent string is a legitimate user agent string. It says Mozilla/4.0, open parenthesis, compatible, semicolon, MSIE 8.0, semicolon, Windows NT 6.1, semicolon, Trident/4.0, semicolon, close parenthesis. Okay, what does that mean? I don't know. And then we have a bunch of other user agent strings. So you might be asking yourself, this browser is telling me something very specific. It's saying I'm Mozilla this version, I'm IE this version, I'm Windows NT this version, and I'm Trident this version. Is there any relationship between, say, the Trident version and the IE version, or the IE version and the Mozilla version? Is there a relationship here? And there's an easy way to figure that out. First, you need to extract these features out. You need to extract this content out so you can do some statistics on them. I'm using a Splunk regular expression field extraction. Regular expressions are a very powerful way to do this. So I have a bunch of field extractions. One extracts the Mozilla version, IE version, Trident version, and Windows NT version. I did this manually in the field of machine learning, a branch of computer science, of what's basically a branch of math and computer science. This is called feature extraction, and it can be automated. So you can extract these features automated. No human being has to do this. But I did it manually because it's pretty easy to do manually for this. Okay? Then I built a contingency table. Splunk has this built right in, but this is a standard statistical thing to do. You can do this in R. You can do this in like 2 lines of Python code. It's really easy to do. So I extract the Mozilla version and the IE version, and I tell Splunk, show me a contingency table for Mozilla version and IE version. Now, let me tell you how to read this table. It's a little bit confusing. So the vertically, that's Mozilla version. So each row corresponds to one Mozilla version, and horizontally, that's IE version. So we have IE version 7, IE version 9, IE version 10, 6, 8. I didn't bother to sort it. Doesn't matter. Okay. So I read the columns down. So Internet Explorer 7, we have, and so this is over, I think, like 31,000 user agent strings or something like that, which is about 20 minutes of data on the network. There are 16,912 things that claim they're Internet Explorer 7, and all 16,912 of them also claim that they are Mozilla 4.0. So, if something says it's IE7, and it claims it's anything other than Mozilla 4.0, it's lying. Because everything that is IE7 says it's Mozilla 4.0. Okay? Let's look at Internet Explorer 10. Internet Explorer 10, we have 24 Internet Explorer 10 hosts that claim they're Mozilla 4.0, and we have 2,842 that claim they're Mozilla 5.0. I think there's 24 hosts that are lying. Now, Internet Explorer 6, we have 1,052 that are claiming they're Mozilla 4.0, 0 that are 5 or 3. So you can look at this table, and you can say, if you're claiming to be Internet Explorer 8, you must also claim that you're Mozilla 4. You can't claim that you're Mozilla 5, and so on and so forth. You can build this contingency table for other pairs of values too. So here's IE version compared to Trident version. So the Trident version is along the top, and the Internet Explorer version is vertically. And so we have a thing that claimed it was, let's take a look at Internet Explorer 9, which is a row. Internet Explorer 9, we have 4,784 of them that claimed that they were Trident version 5.0. We had 22 that claimed their version Trident 6.0. I think we have 22 hosts that are lying. And you can build logic that ties these values together, and in fact, a machine learning model will do this automatically for you, so you don't have to do it by hand. I did it by hand. It probably only took about 15 minutes. It wasn't that hard. So the first part of the query says, give me all the user agent strings and extract all these fields. And then in the bold, the second part of the query is the logic that says, if you claim you're this version, you must also claim these things. If you claim these things, then you must also claim these things. It's just a bunch of Boolean logic that says if you're doing this, then you must be doing this. It's simple assertions. And if you fail the assertion, then you're lying. You're not Internet Explorer. Machine learning can do this all for you. You do not need to write these queries. If you put your logs through some sort of feature extraction and then you have all your features and then you train some machine learning model like a support vector machine, you can get all of this logic automatically and you don't have to see it. I did it by hand because I thought it would be good to demonstrate by hand. Now let's take this query and let's query our network for all the things that claim that they're Internet Explorer, but they got some of the details wrong. They were lying. I know you can't really see the results, but there's like 4 pwned hosts out of the top 10 results that are just like the bad guys took a user agent string that they didn't understand and they went, oh, we probably shouldn't claim that we're Internet Explorer 6, and they changed a 6 to a 7. But they didn't also change all the other values that they should have changed, so it was obvious that they were lying. All right, now, sometimes you can just imagine what bad looks like. So you should ask yourself, what does bad look like? And you only have to come up with one example of bad, and then go, okay, well, let me see if I can create a query that will find something that matches what I'm imagining is bad. So I've shown 4 bad symbols here. Okay, well, okay, maybe there's 3 that are bad and 1 that's good, right? Okay, so should you ever see a Java program download a Windows executable? Well, you should never see a Java program in general. I've been trying to tell people in the company that. They haven't been listening. So this is a very, very simple query. It is like the most generic, brain-dead query that you could ever create for a Java exploit. And it simply says, show me stuff that's using the Java user agent string. And I didn't even bother to fully specify the Java user agent string. I just said Java, somewhere in there, Java. And the MIME type that the web server responded with that was DOS exec, which is a Windows executable. And the URL doesn't contain exe, that limits a few false positives. Let's take a look. I know you can't read this. You're probably not really supposed to read this. But here's 2 results that came back. They were 2 of the results out of 3. And I only looked at like 4 hours of data. Okay, that does not look like a good URL. That's not a usual URL. What the hell is that URL? Okay, I have no idea, right? So you can do your standard investigative procedures, look at the IP address, look at the domain name, that sort of thing. Google these things and see if you can find any information about it. In this case, if you do, you'll find out that it's some exploit kit. I don't remember which one. It's not Black Hole. It's some other exploit kit. Okay, so I'm going to show how to take this from a very generic query to a very specific query. So we have this URL. Let's create a pattern that matches that URL. Okay, so same base query, DOS exec Java, not executable in URL, and then a regular expression that matches the structure of that URL. Now, that URL is super, super random, so my regular expression has to really be very, very, very generic. And I don't know how good your regular expression foo is, but this basically says that I have a whole bunch of random looking things separated by slashes, and I have at least 8 of them, but no more than 32 of them. And then it contains something that a whole string of characters is not a question mark, and then it contains a question mark, and then it contains a string of characters, and then an equal sign, and then a string of characters, only 4 to 8 of those characters, and then an ampersand h equals, and then some numbers, and then it's the end of the string. Could this false positive? If you were just looking at the URL, it could probably false positive. You'd find some advertising network out there that was tripping this. Well, we put DOS exec and Java in the string too. Can this false positive? No, not a chance. This will not false positive. And if you do this query on a big network, I'm not going to tell you how many numbers we had, but just imagine a really big number every single day, and that's how many infections you have with just this one Java exploit. And the cool thing is now you're seeing these machines that are getting infected. You have a set of domains, you have a set of IP addresses, you go through the connect the dots, the incident response investigative procedure. Now you're going to find more patterns based on the malware that was being delivered to these people's machines, more domains, more IP addresses, and you do the rinse and repeat, the iterative investigation, and you follow the graph to transitive closure, and you've learned about tons of different pieces of malware, lots and lots of, you've basically learned about the bad guys that are running this exploit kit. You've learned about their whole operation if you really, really dig into it. That's going to find hundreds of compromised machines on your network. Not only that, but you can then learn about machine compromises in real time. You could even stop them in real time if you wanted, for this specific exploit kit, of course. All right, how about a post to a PHP script? Because bad guys love PHP. They never use anything other than PHP, it seems like. How about a post to an IP address that runs a PHP script that takes a parameter, that means it has a question mark, with no referrer. This can't be a web browser. Well, it could be a web browser, but it's pretty much not a web browser. It's not legitimate anyways. Write a simple query for that. This regular expression just makes sure that there's an IP address in the URL. And you find lots and lots of compromised machines, lots and lots and lots. And they just stand right out as, that looks bad, that looks bad, that looks bad. And you create, simple, you go back through the incident response procedure. You build the patterns. From those patterns, you learn about more domains, you learn about more patterns, you learn about more IP addresses, and you can start to find all of the activity on this network. And if you were recording your logs, you can go back in time, and you can find all of the activity for the last 30 days, 45 days, 90 days. You can go back and get rid of that malware that got by a month ago. And you can learn about all of the other command and control that was being delivered on these machines if you really spend the time to dig through your logs. So this is the idea that will show you the tip of the iceberg, and then your standard incident response procedure will help you map out the whole rest of the iceberg, and it'll give you lots of other ideas for other tips of icebergs that you can look for in your logs. Now, humans are not precision machines. No matter how hard people try, they cannot be precise. Ask a person, do X every Y seconds, and they'll be like, okay, let me look at my watch, and they'll be able to approximate it, and they will not be very good at it. Computers, oh man, no problem. In fact, you tell a computer do something randomly, it will fail. Okay, so here's a graph. I don't know if you can see those green spikes or not. Does that look like human activity? Not really. Okay. Time gaps and statistics are your friend. Take the delta between two timestamps, do your simple subtraction here, and do some statistics. What is the distribution of those time deltas? I implemented this in Splunk. To be honest, Splunk is not the right tool for the job here. It can barely do it. I kind of have to abuse some of the stats, but you can imagine if you're a smart person, you could write some Python code to do this, or you could write a little Splunk plugin or whatever. You could do this. It's not hard. And there's lots of different ways to do it too. So I run this super crazy long query, and all it basically says is, show me the most periodic activity on the network. And I have it sorted here by the average delta, time delta. And the other columns are variance. And the count is the number of times I've seen that query. And this is only a query over the last hour, and I'm gonna show you the top 14 results out of like 200. Almost every one of those machines are either compromised, or when you really dig into what's going on, they're violating some sort of policy. This is a very good way of finding non-human activity. Now, non-human activity all by itself, that's not guaranteed to be malicious. You have to couple this with additional indicators or additional investigation. This will only tell you a human being was not behind the keyboard. It will not tell you that malware was the source, but it's a very good starting point. And there was an excellent presentation yesterday on Twitter bots. And there is a way to detect machine activity, a very, very easy way to do it. You can look at the timestamps, you can look at the distribution of words, you can look at a lot of different stuff. So I took one machine activity, I just queried the network, found something that looked like a machine-like non-human activity, and I graphed it. But I graphed it in an interesting way. Vertically, that's the minute of the hour. So it doesn't matter what the hour is, you just look at the minutes. Horizontally, that's the second of the minute. Does that look random? No. That's a computer. A human will just look like chaos. They'll just be dots all over the place. It'll look like snow. This will not pass a chi-squared test for randomness. you can run statistics on activity. Now, it might not be minute of hour, it might not be second of minute, it might be some other set of axes. In fact, you may do this three-dimensionally. So you may do like hour of the day, minute of the hour, second of the minute. You may do it by like millisecond of the second. There's lots of different ways to slice this, and not all of them have to do with time. And then you can run a chi-squared test. Does it pass some sort of randomness test? Machines will not pass the randomness test, even when they try to, even when they call like R&D and then get a time and then they wait and they sleep that amount of time. R&D won't pass on a chi-square test most of the time unless they're using something pretty good. This will find machines. There's an absolutely fantastic paper on this. It's called Detecting and Analyzing Automated Activity on Twitter. It's an academic paper from some guys out of Berkeley. It's really mathy, it's really cool. It's got lots of pretty pictures that look similar to this. But you can do this at very, very large scales. You can do this for every frickin' Twitter account on all of Twitter at large scales with the right algorithms, and you can find lots and lots and lots of automated bot activity. Now, unless you've been living under a rock, DNS is really, 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 really important. Humans use names. Machines, they can do IP addresses. It also is very good for bad guys because it provides a layer of indirection. So bad guys don't want to use IP addresses because IP addresses are super easy to block. IP addresses are super easy to take down. They want to use names because that allows them to change where the name is pointing to. It allows them to have a little bit of resiliency where they can have one name pointing to multiple IP addresses. It makes blocking a little bit harder because most people aren't very good at blocking names. And it allows things like fast flux where you're constantly changing what IP addresses the names are pointing to. You can rotating it around. So you should definitely capture your DNS queries. And if you're capturing your DNS queries, presumably you're running your own DNS server and you can do that, or you're just pulling the packets off the network and you're capturing them that way, which is how we do it. You should also capture DNS answers, but don't fret if you're not capturing DNS answers because it's a slightly harder problem than queries. There's an organization, DNSDB. It used to be a branch of ISC, the Internet Software Consortium or company, whatever, the guys that make Mind, Paul Vixie and all of the smart guys. They spun off a small little company to do this. And DNSDB.info, you can go and register for an account for free as long as you're a security professional and you can defend why you need an account. They will give you an account. And it allows you to put in a domain name and say, show me all the IP addresses this has ever been seen to resolve to. And Paul Vixie runs FRoot. He knows everything. So this has amazing visibility, a really incredible visibility. It sees just DNS traffic all over the internet. And then the other really, really cool thing is it goes from an IP address to a domain name, but it does it way better than what you host IP address, and it looks up the pointer record for the IP address. It actually does the database query in reverse, so you can get a list of all of the domains that have ever resolved to an IP address. Here's one, I just popped it in. I just picked an IP address out of some of the malware activity that I showed on a previous slide. And then it turns out there's 10,000, more than 10,000 domains. It only shows you 10,000 domains that are running out of that IP address. Maybe that's bad. All right. DNS does not provide you the level of context that, say, HTTP does. It's just a name lookup, and you don't know why the name lookup occurred. In fact, you can sort of force people to look up bad names through no malicious activity. You just put links to bad names in a web page, and Chrome or Firefox or Internet Explorer nicely goes and resolves those names to make sure that it's really ready for when you click on that link so that there's lower latency. So you want to get as much context out of your name lookups as possible. One way to do that is with set operations. So imagine you have two infected machines and you know they're infected with the same set of malware. Let's do a query in our DNS logs, and let's say, show me all of the names that this bad machine looked up, show me all the names that bad machine 2 looked up, show me the intersection of those. What do they have in common? They're going to have lots of things in common. They're going to have your company name in common, they're going to have Google in common, they're going to have Facebook in common, they're going to have tons of things that are in common. So then what you do is you take a good machine, show me all the things it looked up, and you take the subtraction of it, and what's left is that little sliver of stuff that only the two bad machines had in common, but the good machine didn't have, and most of the stuff in there will be bad. And there's lots of other set operations that you can do. Then you can go, okay, well, I have this domain name. What IP addresses has it been resolving to? That's the DNS to DB thing. From those IP addresses, what domain names are there, and you can follow the DNS graph to transitive closure, and you can find tons of bad stuff. Then you turn around, and you go, show me all of the machines that are doing DNS queries to these domain names. And then you turn around and go, okay, well now we have a list of clients. Show me all of the web activity that they're doing on the network. Let's take the intersection of that. Let's find the command and control. You can find bad stuff this way very, very, very effectively. Follow the graph. You don't have to stay within one data source. You don't have to stay within just DNS. You can branch out from DNS. You can go to your web traffic. You can go to your host logs. You can go to your AV logs. You can go to your NetFlow. You can really take this investigative procedure to the nth degree if you have the time to do it. And if you have a good way of querying your data, you can do it quickly and effectively. So the moral of my talk is that if you have a mountain of data, you should definitely mine it. You're going to find gold. Any questions, guys? Yes, sir.
Do you have any opinions or experience with the sharing of indicators of compromise between companies? Or does Cisco, do you guys have enough data that you can just go internally and do it all yourself?
Yeah, so the question is what is my opinion on data sharing across different organizations? Or does Cisco, as a big company, have enough data that we don't have to share? And that's a really complicated question. So there's the stuff that I was talking about here. I wasn't talking about APT. I was talking about typical malware that gets delivered on your machines. We do not need to share these indicators. These indicators are so easy to find. Some reputation feeds, that sort of thing, no big deal. And to be honest with you, it's not worthwhile for me to share, hey, Google, or hey, buddy at wherever, this is a bad IP address, you should look at it, because it's just not worth their time. They have thousands of infections every single day. If they take the time to find one, probably not worth it. When it comes to APT-like stuff, really, really serious bad guys that are working really hard to hack you, it's incredibly important to share that sort of information. And so I think the information sharing for really serious, insidious stuff is very valuable. I think that sharing data for your standard drive-bys is questionably useful unless you have hundreds of infections for it. And that's what reputation feeds really give you. You know, domain name, lists of bad domain names, lists of bad IP addresses. That's more or less data sharing. It's just a feed that you consume and you try to automate most of it. So yeah, the answer is it's useful in some circumstances and not really useful in other circumstances. All right, well, thanks for your time.